a really small part of it, right? It's like, there we are, we're like locally flat, right? Okay, we may never know the true curvature of the Earth because we're just, I'm not sorry, Earth. That, we don't even know that. I guess the Greeks figured that one out, right? We may not know the true curvature of the universe because it's so damn big, right? Did I just cuss on YouTube? I did, I'm sorry. Okay, so this is the inflationary. The question now is, it is big. It is big. How did it get so big, right? And the answer to this is that when it was expanding, when it was tiny, it expanded in the first initial 10 to the minus 43rd seconds, or some crazy amount of like short amount of time. It actually expanded much faster than the speed of light for some period of time. Now think about that. If it expanded faster than the speed of light for some amount of time, doesn't that mean that now it's expanding and there's parts of the universe that are so far away that the universe expansion, space itself, is being created between us and that place faster than light can travel through it? It's like the teacher that assigns homework faster than you can like do the homework, right? Yeah, can you believe him? Right, so anyway, that's the notion. So students always say, well, gee, the universe can't go faster than the speed of light, but that's not true. The universe can expand, like some other part of the universe can be moving away from you because of the expansion of the universe faster than the speed of light. You just can't go through the universe faster than the speed of light, right? So that one part of the song, the Monty Python song, the universe itself keeps on expanding and expanding in all the directions it can whiz. As fast as it can go, the speed of light, 12 million miles a minute, and that's the fastest speed there is a little bit inaccurate because that does imply that it can't expand faster than the speed of light. Indeed, it did many times faster than the speed of light initially, right? And that means that we think we can see a proton's worth of an Earth-sized universe. Yeah? That's crazy. In fact, proton, Earth plus or minus Jupiter. I mean, who knows how accurate that is, right? Okay. So basically, the inflationary hypothesis is the early universe, and by early, not like a billion years ago, but like we're talking like 10 to the minus 43rd seconds or some crazy thing, right? Okay. So it only appears flat. We may never know the true curvature of the universe because we see such a small part of it. Does anybody want some fermented apple cider? Let's see if it's hissing. I think it did. Let's open it up. Let's say somebody was drinking out of this on Tuesday, and they left it in my room overnight, which I'm thinking backwash plus overnight. Even just backwash, makes it unconsumable, but, I'm off camera. Whoever's watching this video is like, he's off camera. It is not necessarily. Yeah, this is what you can do. You get the apple cider. Get apple cider, and I always get like the fresh squeezed stuff, right? And you can actually add a little bit of yeast. Chances are what'll fall in there and react is yeast, right? And then just set it out on your back porch, and just every now and then let the stuff come off, and it'll carbonate it.
What do you mean the stuff come off?
The carbon dioxide. It'll sort of plump up that thing, right? It'll kind of be like this, and then you just let it off like that, right? And it will carbonate it. It will also add a small amount of alcohol. Okay, but it's tasty stuff. Yeah, hard cider.
Where do you get yeast?
Just bread yeast will work, but there's like the people who do it. The people who do it have like a special yeast they use.
Okay.
I think. You can also take your chances on just there being that yeast in there. I did it once and it turned into lovely sparkling cider, and I did it once and it turned into it turned into like nastiness. So it's only yeast is the only thing that does that. Are we right arrow ready? Okay. So if you talk about the age of the universe, it's intrinsically related. Do you see that the slope of this line is the Hubble constant? Does that make sense?
Yeah.
The slope of that is the rate at which the size of the universe is expanding, and so the Hubble constant is this. If you project this thing backwards, if you project the Hubble constant backwards, and you don't add gravitational braking, right, then you actually get an age for the universe if you neglect gravitational braking that's older than it really is, right? If you have a Hubble constant that in other words, if it's expanding very slowly, if we say it's 30 kilometers per second per megaparsec, which is a very low estimate, the universe has to be older for it to have gotten the size it is, right? And if we overestimate, if we say it's like 80 kilometers per second per megaparsec, then this line gets steeper, and we actually underestimate the age of the universe. So this is when they talk about the age of the universe. It's the age of the universe is intrinsically related to the Hubble constant. Is the whole point of this slide, right? Anti-gravity. With anti-gravity, yeah. And so this is the problem, right, is that the type 1a supernovas are too dim. And so what's happening is that the universe is now expanding actually faster than it was previously, right? You know, so there's something going on with that. And it has to do with the fact that we don't know what's in the universe, right? We're missing some of the matter. I meant to drink. Say it again? Okay, well, that's so funny. Left it at home. Never filled it with water, never brought it. So all those memories of me putting it in the car, taking it out of the car, bringing it in, ghost memories. Yeah? What? Habit, yeah, ghost memory. I remember doing that. It's like attendance. If I remember what you look like, I think you're here. It's called ghost attendance.
What do I look like?
I have no idea. Redhead. I was going to say redhead dude. Glasses. Sassy.
Glasses only look sassy.
Looks sassy, is sassy. That's a pretty good description. Okay. Da-da-da-da. And then the age of the universe. This is good news. For a while, stars were 15 billion years old and the universe was 12 billion years old, right? And people were like, no, that doesn't work, right? It's like, you know. But as far as we could tell, the oldest stars are about 13.7 billion years old, roughly, right? Nuclear decay suggests also an age around 13.7 billion years. The deceleration, the expansion, the flatness, all this stuff is centering in. And so it used to be that the universe was 15 billion years old, 10, 12, 15, right? You just sort of read a different age, you know, plus or minus. It's 12 and a half, plus or minus 2.5 billion years, right? You know, but due to, you know, taxpayers' money spent on basic research, the Wilkinson microanisotropy probe we've really nailed it down, right? In fact, I'm sort of nervous that they're saying this is plus or minus 0.2. It's like, that's a little bit dodgy, right? Okay, so problems of the Big Bang. What are the problems that we haven't figured out yet? We'll start with the biggest one. As far as we can tell, what we can see is about 10% of what's there. The Wilkinson microanisotropy probe put this at about 4%. I prefer to say 10%. Yeah? Better to not know about 9 parts in 10 than to know about more than 19 parts in 20, you know? I just think. I'm sticking with the 10, right? The problems of the Big Bang, we don't know why the expansion rate has started to increase. Gravity should always make it slow. Maybe not enough to make it ever stop or bring it back together, but gravity, like me, is an attractive force of the universe, correct?
Yeah.
So gravity should make it slow down. If it's increasing in expansion rate, there's something else going on. There's another guy in town besides gravity, and we don't know who he is, or she, right? So when we look at galaxies, right, when we look at the motion of galaxies, we can do a simple calculation. You guys did it last year, and it's the gravitational calculation of orbit, right? So you set centripetal force equal to force of gravity. You solve for how long it should take them to rotate. We can look at galaxies and measure their rate of rotation. You can see it in their spectral lines. Okay? So we know how fast they're rotating, and all of them are rotating way too fast. What does that mean? That means there's way more attractive force in that galaxy making it spin really fast. Like IBII Park, right? You pull yourself in, harder you pull yourself in, the faster you spin, correct? Yes, does this make sense? Okay, so if we look at the galaxy, we can calculate that inward pull, that force of gravity, because we can count the stars. 1, 2, 3, 4, rather a graduate student can, right? Using statistical methods, count the stars, and we know the size of every star because of its brightness, right? There's a brightness-size relationship, which really is not size but mass, right? Okay, And so we can look at that, and the part of the galaxy that's emitting light is not nearly massive